Hello and welcome. It's a pleasure to be asked to talk at the London Theory Institute. I'm going to tell you the answer to the question, what is an anomaly? As I'm more of a physicist than a mathematician, I'm going to proceed by examples. The first part of the lecture, I have a number of quantum mechanical examples, which I hope will be fun to work through. And then at the end of the lecture, I'm going to move into the field theory context, which might be more interesting to the people in the audience. All right, so let's get started. What is an anomaly? So I'll go ahead and just answer that question before we do anything else. An anomaly is a classical symmetry that is broken by quantum effects. In view of many recent developments in the field, I feel like this is not a particularly good definition anymore. It's one that worked in the old days, 20, 30, 40 years ago, but as people look at more exotic kinds of anomalies, these higher form symmetry anomalies, various kinds of global anomalies, discrete anomalies, it seems to be a definition that's kind of getting stretched to its breaking point. And that's part of the reason I'd like to proceed by example, so that you sort of see this, a little bit of the scope of the behavior of what an anomaly is, and that may give you a better sense than a formal mathematical definition. Okay, but before we get into anomalies per se, let's talk about other ways of breaking symmetries. There are usually three ways that us physicists like to think about, three ways of breaking a symmetry. The first is explicit, the second is spontaneous, and the subject of this lecture, anomalous breaking. And let's take a very simple example, actually a classical physics example to start out with and just refresh our memory of what these different concepts are. So a classical example. We're going to take a massive bead on a wire, a circular wire. So here's my circular wire. It's going to have a radius r. Here's my bead sitting on that wire, and I want to measure the angle. I'll parameterize that bead by an angle where it is on the wire, by an angle. It's going to have a mass m. And so let's start by writing a Lagrangian for such a system. So the Lagrangian, as you well know from your undergraduate studies, I can write in the following form. It just has a kinetic term at this point. So theta dot is the time derivative of the angle. So it just has basically a mass times a v squared term in the Lagrangian. Now, what kinds of symmetries does this system have? Well, the way I've written it, it's got two. It's got a SO2 rotational symmetry, under which we shift theta by a constant angle. And because alpha is constant, it doesn't affect the Lagrangian, so that's a symmetry. And there's also a Z2 reflection symmetry, under which we send theta to minus theta, and then because the action involves just theta squared, or actually theta dot squared, again, the Lagrangian, or the action, is invariant under that reflection. So we have these two nice symmetries that we can think about in this classical system. Now the first thing I want to do is I want to break the symmetry explicitly, the rotational symmetry anyway. So an explicit breaking, we will introduce a gravitational field, parameterized by that acceleration, g, and we'll also spin the wire around its vertical axis. So we're going to introduce a rotation, omega, of the wire, so it's going to be spinning like this. And when I do this, the Lagrangian is going to change. It's going to develop some potential terms. So I still have the kinetic piece, and I'll develop a potential term due to the spinning. I guess I can also think about that as a kinetic term, but since I'm doing this kind of externally, I'm externally rotating it, I can think about it maybe more accurately as a potential. And I also have a potential due to the gravitational field, mgr cosine theta. And you notice when I've added these potential terms, I no longer have the rotational symmetry. So the rotational symmetry is broken explicitly. However, the way I've done this, I still have a Z2 reflection symmetry that's preserved. The potential hasn't broken that yet. Okay, so explicitly, I can break the symmetries just by adding extra terms in the action or the Lagrangian. So the next thing we want to do is we want to break that symmetry spontaneously. So spontaneous breaking, and this is going to happen dynamically. This happens when the ground state of the system does not preserve the symmetry of the Lagrangian or the Hamiltonian. So the ground state does not preserve the symmetry of L. or more generally S. So let's see what happens with this case. So let's copy that Lagrangian from the previous page. So there it is. And I want to look for a ground state, or the lowest energy state. So in the lowest energy, I won't have any kinetic energy. So let's set theta dot equal to 0. And to satisfy the equations of motion, then I need to make sure that dl d theta equals 0. Or in this particular example, I need to see that m omega squared r squared sine theta cosine theta minus mgr sine theta equals 0. Or we can simplify that a little bit. The equivalent condition is that sine theta times omega squared r over g cosine theta minus 1 equals 0. And so there are clearly two solutions here. To find a critical point, we can set theta equal to 0, or actually more generally pi times some integer, although we're going to find that the 0 one is the minimum. And another case that we can do is we can set cosine theta equal to g over omega squared r, which of course only makes sense if that constant on the right-hand side there is less than 1. Okay, so let's draw the potential in these two cases, and we'll see what's going on. It really is basically like that Mexican hat potential you're familiar with from the usual spontaneous symmetry breaking example. Okay, so here's case 1, omega squared r over g less than 1, so there's no solution for that cosine. And lo and behold, there's a single minimum, stable minimum for the mass sitting at the bottom of the ring. And then there's another case if it's spinning fast enough where I do have a solution for that cosine. Omega squared r over g is greater than 1. So here we draw it again. And now there's a pair of minima. And the bead should choose one of them. And when it does, because now I've broken that theta to minus theta symmetry, that remaining discrete symmetry that wasn't broken explicitly, I have spontaneous symmetry breaking. All right, this is probably familiar to many of you. Maybe I'll make that bead a little bit clearer, make it red sitting there at the bottom. I want to make a few remarks before I move on here. Remark 1, this has been a classical analysis. If we were to look at this quantum mechanically, there's no spontaneous symmetry breaking. And why is that? Well, it's because the ground state, GS for ground state, I could take as a superposition of, maybe this is not an exact statement, but it's almost true. In the limit where the potentials are, the minima are well separated, I take that sort of classical minima on the left and that classical minima on the right, and I take a linear superposition of those two classical minima, and that's a very good approximation to the true ground state. That there's some tunneling between these two minima that can lower the energy. So that's the quantum mechanical situation. We can also think about the quantum field theory situation. In that case, we do have spontaneous symmetry breaking. The reason for that is that we want to promote theta of x to a field of some auxiliary set of variables, not just time. And now because this field exists throughout space, it's too hard to tunnel all at once. And there's no good way for the system to reduce its energy by taking this linear superposition. Now, the remainder of this first part of the lecture, I want to give you a more complicated example where anomalies actually are able to guarantee a degenerate ground state. This is going to be a related quantum mechanical example as we go forward where anomalies guarantee a degenerate ground state. So this is maybe much less familiar. Good. Okay, so that's the introduction of my lecture, and now we're going to move into our first real example of an anomaly. We're going to stick with this bead. We're going to make the bead charged, and we're going to introduce a magnetic field. And the kind of picture I want you to have in mind is here's my bead on the circular wire, and in the center of this system, I'm going to introduce a constant B field, some magnetic flux through the center. So where the bead is moving, there's actually not going to be any magnetic field at all. But because there's that magnetic field in the center, there's actually going to be some effect on the wire, residual effect. It's like an Aharonov-Bohm effect. So in this case, the bead doesn't experience a magnetic field, but it does experience a vector potential. So I'll introduce a parameter gamma, which is going to be proportional to this vector potential. And in this situation where the magnetic field is inside the loop, it's going to be constant. And I'm going to assign an exercise a little bit later on where you can work out some of the details of this for yourself. But for the moment, let's just take for granted that this system is described by the following classical Lagrangian. So I have my old kinetic term, 1/2 theta dot squared. There should be an m and an r there also, but let's just set that to 1 to make our life simple. And now I have the effect of my magnetic field, which I'm going to parameterize with this constant gamma. All right. Sorry, this should be squared, of course. 1/2 theta dot squared. It's still a kinetic term. So again, this is a constant B field inside the wire. All right, so let's talk about symmetries. I still have rotation because the Lagrangian only depends on the derivative of the angle. So I have a rotation SO2 under which I can send theta to theta plus, let's call it delta, the shift. And what about that reflection we talked about before, the Z2 symmetry? Well, that seems to be broken, but it turns out that for certain specific choices of gamma, I can keep the Z2. So if I tune that magnetic flux through the loop in exactly the right way, so that gamma takes on the right set of values, I'm still going to have a Z2. So let's see how that works. This is a quantum effect now. So this is one way in which this definition about classical symmetries being destroyed by quantum effects gets a little bit sloppy already, because this Z2 symmetry is now already only sort of there because of quantum effects. But let's just see how it works. So we need to broaden our perspective here to see how this reflection symmetry persists. So what's our quantum perspective? Let's talk about the path integral. So the path integral for this theory, right, I have to integrate over all possible configurations, angular configurations. I've got an integral e to the I L of t dt. And now from this perspective, it's clear that for there to be a symmetry in the path integral, L of t dt doesn't need to be invariant, but it does need to be invariant up to a shift of by 2 pi times an integer. So it needs to be invariant only up to a shift by 2 pi times an integer. Okay, that's the first non-trivial statement. That's a little bit outside the classical scope here. It's something that's coming from quantum effects, from the path integral. And now there's another key assumption, which from time to time makes me unhappy when I think too carefully about it. But here it is. It's a very powerful assumption. It's very useful in many cases. It's an assumption that the theory should make sense on any space. So the space here is just the time coordinate, and we're used to thinking about time as just some line, some linear variable. But here what I want to do is I want to think about it not as a linear variable, but I want to compactify time. I want to identify time up to a shift by some constant t. So now I'm on a loop, and I want to claim that my theory should make sense on this space. So in order for that to be true, theta also is an angular variable. It means that if I evaluate theta at t, so I go around the loop, I'd better come back to the same angle. But of course, since the angle is only defined modulo 2 pi times an integer, I only need to get back to myself up to 2 pi times that integer. Okay, so if that's true, now let's analyze this problematic term that seems to be breaking that reflection symmetry. So I had this gamma theta dot term, which doesn't seem to behave well under theta goes to minus theta. It's a total derivative since gamma is a constant, so I can evaluate it now on my compact time circle. And what do I find? I find that I'm going to get gamma times 2 pi times that integer n. Okay? So what does this mean? This means that if I shift gamma to gamma plus 1, this is a sort of a symmetry. This is a sort of a symmetry of the theory. I'll put it in quotes, since maybe it doesn't fit with all the sort of standard definitions of a symmetry that you're used to, but it takes the theory back to itself. It just shifts the path integral by this phase. And so it leaves things invariant. So if you've had a good quantum field theory course and you've talked about QCD and Yang-Mills theory, you may have seen something very similar to that, to what we're discussing here in that context. You might have seen this theta angle term, this f wedge f times a constant theta, which also has a sort of similar symmetry because f wedge f gets quantized in a similar way. So there's some very close connections between that system and this. Okay, so that was a sort of quantum perspective interlude, and now let's get back to this reflection symmetry. Is it there or isn't it there? Back to Z2. So I want to send theta to minus theta. So what does this imply about the shift of that problematic gamma theta dot dt term? Well, it's just going to be 2 because I'm going from theta to minus theta, so I pick up a factor of 2 times gamma times 2 pi n when I do this integral, knowing that it's a total derivative and theta has to be periodic as I go around the circle. So in order for this to be a pure phase, in order for this Z2 to be a symmetry, I find I have a symmetry for two cases, gamma an integer or gamma a half integer. And then because I have this sort of symmetry in quotes under shifts of gamma by an integer from 1 to 2 to 3 to 4, really there's only basically two cases to analyze. All the others are equivalent. There's the simplest case where gamma is 0, and there's the slightly more complicated case where gamma is a half. Okay? So the claim is in these two special cases, and all cases related to those by shifts of integers, this Z2 symmetry is still there in this sort of secret quantum way. But it's not there comfortably. There's an anomaly. It's a special kind of anomaly, often called a Tuft anomaly. There is a Tuft anomaly with the Z2, and in fact, it's not really possible to separate it from the rotational symmetry either. The Tuft anomaly inextricably mixes these two in this kind of problematic way, as we'll see in a moment. So what is a Tuft anomaly? These are anomalies that show up in global symmetry. So these are global symmetries, these Z2 and SO2, when you try to gauge them. So what do I mean, gauge a global symmetry? Well, I mean, so for the rotational symmetry, instead of meaning that I shift theta by the same amount for all time, I want to shift it in an amount which depends where I am, or where I am in time. And when I do that, in order to compensate for that time dependence in the shift, I need to introduce an external gauge field. And the way this works is that I see the anomaly when I turn on these external gauge fields. So let's see how this works. So let's gauge the SO2 rotational symmetry. So I have a ddt, and it's going to become a covariant derivative after this weak gauging. So instead of ddt, I'm going to have ddt minus a gauge connection A of t. This has nothing to do with the magnetic field I was talking about before that I was using to set up the system. So under this, I can shift theta to theta plus delta of t now. Delta is a function of t. And to compensate that time dependence, I now have to shift the vector potential in a time-dependent way as well as the time derivative of that delta of t. And of course, in this combination, then the covariant derivative becomes gauge invariant, doesn't shift under this combined shift of a and theta. Okay, so let's see what happens to L under this shift. I think I should start a new sheet of paper here. So L, under this weak gauging, wherever I had a time derivative, I now also have to include this vector potential. So the kinetic term gets an extra piece. This gamma term gets an extra piece. And now it turns out it's useful to add one more piece here that depends just on the vector potential. This is what's called a counter term. And it would be very nice to do this in some kind of gauge invariant way. So let's think about whether this addition here is gauge invariant before we do anything else. So what changes under gauge transformation? So if I take delta of this, delta of k, a of t, dt in the action, I can write this as minus integral k delta prime of t dt, which is minus k delta of capital T minus delta of 0, again thinking that I'm living on some compact time circle. And then finally I get minus k 2 pi n, because I'd better shift things in a way that's compatible with the periodicity. And if I'm going to shift theta by this gauge parameter delta of t, by the time I go around the circle, I better shift the angular variable by 2 pi times some integer, or I'm not back where I started. It doesn't make sense. I don't have a good winding number for the theta angle. Okay, and now for this to be a phase in the path integral, for this to be a pure phase, I must require that k is also an integer. So I can add this counter term in a gauge invariant way, but k must be an integer. What happens to the Z2 now that I've gauged the rotational symmetry? So I had a theta goes to minus theta. So now this looks really bad. It doesn't look like the same Lagrangian at all, but maybe what I should do is I should supplement this symmetry transformation on theta with a symmetry transformation on the vector potential, since it's a new object. It wasn't there before. Maybe it also should transform under this Z2. So let's send it to minus a of t. That seems reasonable. Seems like some kind of charge conjugation maybe, in a more traditional context, where you're like taking a complex conjugate of the field. Theta is really the phase of some field, so complex conjugate sends theta to minus theta, and it also, there's a charge multiplying the vector potential, so that charge got sent to minus q. So it's really sort of like a charge conjugation. Anyway, what happens when I do this? Well, The first term, the kinetic term, is fine, right, because it's quadratic. But this gamma term is a little bit problematic. You know, we already discussed how this gamma theta dot piece is okay, because it's just going to shift by a total phase. But now we have a new piece here, this vector potential piece, which doesn't look like it's going to behave well under this shift. So let's see what's going to go wrong here. So when I do this shift, I'm going to pick up two contributions. I'm going to pick up a contribution from this gamma term, and I'm going to pick up a contribution from the counter term, integral a of t dt. This will be my shift in the action. And now it's no longer clear that, you know, the integral of at should be quantized in any nice way. And so in order for this to vanish, I really need this combination gamma plus k to vanish. But I can only arrange this in one case, right? I mean, in order to arrange this to work, I need to be able to set gamma equal to minus k, and I can only do this if gamma is an integer. If gamma is not an integer, in order to preserve gauge invariance, k has to be an integer. So I'm faced with this rather annoying choice. I can either preserve the gauge invariance, or I can preserve the z2, but I can't do both at the same time. So if gamma is an integer plus a half, there's no way to choose k consistent with gauge invariance. This is the anomaly. So if this sort of path integral Lagrangian approach to it was a little bit uncomfortable, I'd like to kind of revisit things from a more traditional Hamiltonian quantum mechanics viewpoint now, which hopefully will shed a little bit more light on this example and also show us how anomalies can give us degenerate ground states in quantum mechanics. So we had our Lagrangian, 1/2 theta dot squared minus gamma theta dot, and we need a Hamiltonian. So let's see how that works. So we've got a conjugate momentum p, which is dl d theta dot. That's nothing but theta dot minus gamma. And so our Hamiltonian, which is p theta dot minus l, that's also known as theta dot minus gamma times theta dot, minus 1/2 theta dot squared plus gamma theta dot. And the only thing that's left over when the dust settles is 1/2 theta dot squared. So that's our Hamiltonian, but of course we need to express it in terms of the conjugate momentum, which in this case is p plus gamma. Right, so I'm going to get from my Hamiltonian p plus gamma squared times a half. And I have a little exercise for you, the first of many, which is to derive this Hamiltonian from the physics of a charged bead moving around some magnetic flux, and also constrained to this circular wire. So the idea of this exercise is to try and figure out what the constants are, is to figure out how the magnetic field and the charge and the mass and the radii go into setting the constants in this Hamiltonian. All right, but anyway, that's an aside. We have this Hamiltonian, we can use it, and we'll promote it to a quantum mechanical one, an operator on a Hilbert space. We'll trade in our momentum for a theta derivative. This is the momentum, angular momentum going around the ring, and that's just controlled by this dd theta term if I set the masses and so forth in an appropriate way. Okay, so this is the Hamiltonian I'd like to use. So the first job is to figure out the spectrum and the eigenstates. So I claim that the spectrum has a relatively simple form. It's just an integer plus this gamma squared. So these are my energies. I'll call them En comma gamma. And my wave functions, theta n, my normalized wave functions, they're just plane waves going around the ring. And n here is any integer, positive or negative, including 0. So this is a way of diagonalizing my Hamiltonian. And I've set this, of course, by insisting on periodic boundary conditions for my wave function, that I go around the circle and I get back to where I started. So the first thing I want to note about the spectrum is that it has a sort of self-similarity or a symmetry that if I shift n down by 1 and I shift gamma up by 1, I get the same energy back. And so this is another manifestation of what we saw a few pages before, that gamma goes to gamma plus 1 is a symmetry of the system. In particular here, it's a symmetry of the spectrum of states of the Hilbert space. Of course, I require here having an infinite set of states, that goes all the way from n equals minus infinity to n equals plus infinity. So gamma goes to gamma plus 1 is a symmetry of the spectrum of states. So now let's think about how our Z2 symmetry and our rotational symmetry act on the spectrum. Okay. So for rotation, let's introduce the generator R alpha as a shift on theta by a constant alpha, and I'll introduce a reflection, Z2, we'll call that C, maybe to suggest charge conjugation as theta goes to minus theta. So this is clearly a symmetry, the rotational one, and the Z2 one, of course, is not obviously a symmetry. This is a more subtle case. It's only sort of clearly a symmetry when gamma is 0, and the Hamiltonian is then quadratic in theta dot. But the claim is that it's also going to be a symmetry when gamma is half integer. So how do we set things up? The action on states, so R alpha is going to shift theta by alpha, and so it shifts the state by a phase, e to the I n alpha times n. Now when gamma equals 0, C acting on the state n pretty clearly produces the state minus n. To get a symmetry on the set of states when gamma is equal to half, I've got to do something a little bit more tricky. I've got to set n to minus n, but also shift by 1. And the claim is under this additional shift by 1, I can see that all the states are paired up in this way, that I'm shifting a state to another state with the same energy. And in particular, I've got two degenerate ground states in here. 0 and 1 are degenerate ground states. All right, now our external gauge field argument from a few pages ago, that there was some kind of anomaly, some kind of Tuft anomaly, it suggested a non-trivial interplay between the rotation and the charge conjugation, at least when gamma was half integer. So let's see what happens. So if I take gamma equals 0, let's see what happens if I act with C R alpha C. So I conjugate the rotation by the action of the C2 symmetry. So this should work. There'd be nothing subtle here. So I go C R alpha, I get minus n. I act again with the rotation, I get C minus I alpha n minus n. And then I act one final time with C, and I get e to the minus I alpha n. I can just commute the C through the phase. And this is the same as the action of R of minus alpha on n, which is consistent with our geometric intuition for what should be going on here. Now if I take gamma equals 1/2 instead, and I go through the same exercise, now I get R alpha minus n plus 1, C e to the minus n plus 1, and then the state is still minus n plus 1, and then I act again with C, I'm going to get E minus n plus 1 alpha I n. So I get the original state back again after acting with C twice. C should square to the identity. And this I can interpret as e to the alpha I r to the minus alpha n. So I don't quite get what I would expect geometrically. I don't quite get the opposite rotation by minus alpha. I get that up to this phase e to the alpha I. So what does this mean? It means basically I have different groups here. At gamma equals 0, I have more or less exactly what I would expect. SO2 cross Z2 combined to give me some double cover of SO2, I get O2. But at gamma equals 1/2, there's this new central element. I call it central because it's just a phase. It commutes with everything else. It's just e to the I alpha. And, well, we could try to define it away, see what happens. Maybe we could define a different rotation element, R alpha tilde, which is R alpha e to the minus I alpha over 2. And then indeed, when I do this conjugation, C R to alpha tilde C, I get R minus alpha tilde without that extra phase, which is what I'd like. But now a rotation by 2 pi is no longer the identity, it's minus 1. So I've got to go around 2 pi and then another 2 pi to make 4 pi to get the identity. So what I'm finding here is I'm finding a double cover of O2, which has a name. It's called pin 2. And so indeed, in this gamma equals 1/2 case, there is some non-trivial interplay between these two groups, the reflection symmetry and the SO2 symmetry. So this is another manifestation of the anomaly, although again, you sort of see the difficulty with this initial statement of what an anomaly is, that a classical symmetry that's broken by quantum effects here in this discrete context where some of the symmetries are discrete, one could arguably say that I'm not reducing the symmetry, I'm finding more symmetry, I'm finding some enhanced group, although that's not quite the right way to describe what's going on. Okay, so we're almost at this point about degenerate ground state, so let's get there. So we don't need the full SO2 to talk about this anomaly. We could just keep a Z2 in the SO2, just say a rotation by pi. And the way we'll do that is we'll have some explicit breaking, like we did in the original example in these lecture notes where we have this gravitational potential and the spinning wire. So we can imagine adding a bunch of cosine terms. But I'm going to do it in a special way. I'm going to add only even integers. And if I do it in this way, I'm going to preserve both the reflection symmetry and this remaining Z2 symmetry in the rotation group, where I shift by pi. And now we have our second exercise, which is to show that these three elements, e to the I pi, the central element, a rotation by pi, and this charge conjugation, or Z2, that the three of them together generate the dihedral group D8. And then what we see here now is that because we have this group with irreducible representations that are larger than one-dimensional, we see that these three elements, e to the I pi, r pi, and c, they act on our degenerate ground state in this gamma equals 1/2 case as a two-dimensional irreducible representation of D8. So there's some consequences of this. One is that there's no way for the degeneracy to be lifted, no way consistent with the symmetry. So as long as that D8 symmetry is there, I have a degenerate ground state. And this usual story of a unique ground state in quantum mechanics fails. You can look at more detail in this example, and the tunneling amplitudes between these two degenerate ground states, it vanishes. Now, what happens in the usual case, right? I just maybe have a Z2 symmetry acting on the ground states. I just have say two ground states which are equivalent. And Z2, of course, has only one-dimensional irreducible representations. And so I can, if I have those two states, I can make a lower energy state by forming some combinations which give me one-dimensional representations of the Z2. But here, since the ground state transforms under this two-dimensional representation, nothing I can do. I'm guaranteed to have this degenerate ground state. So that brings me to the end of the first part of this lecture, and I wanted to make a few remarks about why I went through this example in such detail. So I drew it largely from a reference by Gaiato, Kapustin, Komargodsky, and Seiberg. So if you didn't like the way I discussed it, you can find a nice patient discussion in their appendix, I think Appendix D, where they go through this same example. And the reason they went through this seemingly simple example is they were interested in applications to Yang-Mills theory and QCD. So there's a lot of similarity here between this parameter gamma and the theta angle in Yang-Mills theory. And they're able to bootstrap off this simple quantum mechanics example and they're able to deduce aspects of the phase diagram for Yang-Mills. And optimistically, maybe you could push this a little bit further and talk about QCD as well. All right, so that brings me to the end of the first major example in this lecture. If you stay around, I'm going to discuss another quantum mechanics example next, and we're going to start talking about my favorite kind of anomalies, which are anomalies in scale symmetry. So this is the second example in this lecture. It's going to be an example of a scaling anomaly, an anomaly in the scaling symmetry, and it will be again a quantum mechanics example. Now, these scaling anomalies are much closer to my heart than the anomaly we just discussed in the last half hour or so. These are kind of anomalies that I've looked at in great detail in my own research, and so I'm looking forward to sharing a particularly simple example of its manifestation as we go forward. So here goes. Scaling symmetry anomaly in quantum mechanics. All right, so here's my Schrodinger equation that I want to solve. It's going to be a 2D scattering problem. So I have a kinetic term, and I have a very simple potential term. It's going to be a Dirac delta function, And I've written it with a negative sign there because I have in mind at the end of the day this lambda is going to be a positive quantity. So it's going to be attractive delta function. So that acts on my wave function, psi of r, and it's going to spit out, if I have an eigenstate and energy, E times psi of r again. Now, a curious thing about this particular Schrodinger problem is that it's invariant under scaling, at least naively. So it's invariant under rescaling the position by a constant a, and at the same time rescaling the energy by 1 over a squared. So what does this mean? Well, from a quantum mechanics point of view, it's a little bit sick. There's going to be a continuous spectrum. If we have some energy state, we have all other possible energy states related by rescaling by this positive number a squared. In fact, if there exists a single bound state with negative energy, we're in trouble, because then the Hamiltonian's unbounded below. There's a continuum, and the energy can run off to minus infinity. So that's something that we need to be a little careful about moving forward. So let's try to reveal the anomalous behavior of the system through a scattering experiment. And to do that, I need to review a few facts about scattering and quantum mechanics, which, if you're like me, you studiously ignored the first time you took a quantum mechanics class. So the first thing to do is a review of 2D scattering off a localized potential in quantum mechanics. So this is almost certainly something you didn't do in the main lecture in a quantum mechanics course. If you took one of my courses, you may have seen it in a homework assignment, but usually people only talk about 3D scattering or maybe 1D scattering, very rarely 2D scattering, and then often it's skipped entirely. So anyway, let's talk about 2D scattering. So I want to write a form, asymptotic form for the wave function. So I have my incoming plane wave. I'm going to send in some incoming plane wave in the x direction, and it will scatter out in a way that depends on the angle. In 3D, there'd be an extra angle, potentially if the potential wasn't symmetric. Here I just have an angle, one polar angle describing the angle around the target, and a radially outgoing wave. So this is incoming. This is my boundary condition, if you will. And this is what happens. This is the scattered stuff coming out. So a couple of remarks about this particular asymptotic form. So this is a large R form for my wave function. First remark is that this f of theta has a classical interpretation as a differential scattering cross-section. Its amplitude, if I take f of theta absolute value squared, this is the differential scattering cross-section. Let's think about that e to the I kr piece that I wrote down. The presence of k in the exponent, this is indicating I have energy conservation. So I have the same energy waves going in as going out. Remember, far from the potential, I should be back to a free theory. And so the energy is just h bar squared k squared over 2m. So I should find the same energy in these particles that I send in that come out. And then finally, that 1 over root r, this is just probability conservation. I want to make sure when I integrate a shell around the target that, I've got the same amount going in as going out. And so that 1 over root r squares to make 1 over r, which cancels the growth in the area of a spherical shell, right? Okay, so we're going to solve this Schrodinger problem. That was my review. Now we're going to solve this Schrodinger problem in momentum space. So I have my Fourier transform wave function, which I'm going to write as d2x, e to the minus I p dot x, psi of x. Remember, I'm in 2 dimensions here. It's because of this transformation of the delta function, right? If I were in 3 or 1, then I wouldn't have the scale invariant. So this scaling is a peculiar feature of the 2D system for the delta function potential. All right, and so what do I get? I get p squared over 2m for the kinetic piece in the Schrodinger equation. When I go and Fourier transform that delta function, I just get lambda. I get a Dirac delta function. I get to evaluate the Dirac delta function at r equals 0, and so I get the un-Fourier transformed wave function evaluated at 0. And on the right-hand side, I get the energy, right, which I said was h bar k squared over 2m, and I'm just going to set h bar equal to 1 here, so I don't have to worry about it. So there's my Schrodinger equation in momentum space. So now I can solve this for psi, and there's a piece that's easy to see is there. This is just solving it algebraically, but there's also kind of a kernel here, and so there's a little bit of flexibility in how I solve it. I'm free to put in a kind of homogeneous part that's going to give me the right boundary conditions. So I can put in a p minus k delta function that gets annihilated by this, this equation on the second line. And I'm putting this in to get out my incoming plane wave, to get the boundary conditions, to get the e to the I kx behavior. Right, so my k vector, that's a vector that I've chosen to be in the x direction, and it's picking the incoming wave that's scattering off my potential. Okay, so here's my solution in momentum space, and now I Fourier transform back. I get psi of r equals e to the I kx plus 2m lambda psi of 0 integral d2p 2 pi squared plane wave factor p squared minus k squared. So that formally is my solution. And now there's some problems with it, as we'll see going forward. So let's copy that and go to the next page here. So this needs to be consistent, right? There's a psi on both sides of the equation. So let's make sure we can have a consistent solution here. So evaluate it at 0. What do we get? We get psi of 0 equals 1 plus 2m lambda psi of 0 integral d2p over 2 pi squared, 1 over p squared minus k squared. Now this looks problematic because that integral is log divergent. So we're cruising along nicely. We've done the Fourier transform, we Fourier transform back, we found a potential solution, and now consistency is getting us in trouble. We're finding this integral over all of the states that's log divergent. So we need some way to deal with this. I mean, we can throw up our hands and say, well, it was a sick theory, or we can say, well, maybe we can still save it, maybe we can regulate it in some way that won't affect the physics too much. So what we're going to do here is we're going to regulate with a cutoff. We're only going to integrate up to momenta less than lambda. And when we do this, we can evaluate the integral. It's just a logarithm. You get 1 over 4 pi natural log lambda squared minus k squared over minus k squared. And we're almost done now. So that gives us psi of 0. And now we also need a solution. And to get the solution, we still need to do the full integral. Well, I'll just point out before we leave, of course, that, introducing this cutoff also introduces a scale. This is our anomaly. This is our scale anomaly, that we're, quantum effects, doing this quantum mechanical scattering effect. We find this infinite integral over momenta, over the states. To be able to deal with this, we have to introduce a scale. Okay, but let's keep going. Let's see what happens. Maybe we can make a little bit more sense of this going forward. Let's try and get this full integral done and find a solution. So we have integral d2p over 2 pi squared e to the I p dot r over p squared minus k squared. So the usual way to do this is to go to polar coordinates, or at least the way I typically do it. I still have that factor of 2 pi squared from the momenta integral, and now I have e to the I p r cosine theta over p squared minus k squared. So the theta integral can be done to give a Bessel, and then the Bessel can be done to give a Hankel function. It's a little bit of work. I leave it as an exercise, although not a formal one. And here's my outgoing Hankel function that comes out of the integral. It's good as outgoing, right? Because we want the waves to scatter off of this target. And to compare with this, asymptotic form for the wave function that we had before that had this f of theta, we should look at the large R behavior. And when we do that, we find 1 over 2 square root 2 pi e to the I kr plus I pi over 4 square root of kr. And so what does this imply? This implies f of theta, just reading off, comparing the form of the wave function we found to the form we wrote down at the beginning, that this scattering amplitude is m lambda in the numerator, 2 pi k square root in the denominator, the value of the wave function at the origin, e to the I pi over 4. So a couple of remarks. There's no theta dependence. This is pure S-wave scattering. As you might expect, it's a delta function. There's no breaking of that angular symmetry. So what goes in gets scattered out in a theta independent way. And then the second comment is that there's a pole in the scattering amplitude in f of theta. There's a pole in f of theta because there's also a pole in psi of 0, as we saw in the previous slide, and that this indicates a bound state. At least that's the usual logic. So let's look at that. So If I go back a page, you see what we had here. We had psi of 0 expressed implicitly, and we had the value of the integral worked out. And so what I'm going to do is I'm going to move psi to one side, the integral to the other, and we'll see what psi looks like on the next page. So here I am. I'm solving for psi of 0 now, writing down the answer in terms of our cutoff that we added by hand. And indeed, right, we see that there's some kind of pole here for specific values of k. There's a pole at k squared equals lambda squared over 1 minus e to the 2 pi over m lambda. And so this is going to be a bound state, k squared less than 0, for m lambda greater than 0, which, as I discussed at the beginning, was an attractive delta function. The positive lambda corresponded to an attractive delta function. For m lambda repulsive, this is attractive, which is m lambda less than 0, you're free to send the cutoff off to infinity, and psi of 0 to 0, and no scattering. So the repulsive case, the repulsive delta function case is sort of consistent with scaling symmetry. But for the attractive case, it seems like, to make sense of it, you'll find potentially this bound state, which gives you a resonance in the scattering. So indeed, we can trade lambda for the bound state energy, which, if we're actually trying to model something experimentally, maybe this can be experimental input, and then hopefully, just with these couple parameters, you have a good model of your system. Or alternatively, maybe you have a different way of thinking about the delta function at very short distance scale. So remember, this is a problem when the momentum goes off to infinity, or correspondingly when you're probing distances that are very, very close to this Dirac delta function. And physically, it's a bit of a singular object, right? This Dirac delta function. So maybe if you're actually modeling some real physical system, you have in mind it has some width. Maybe it actually looks like a little well or something, which might actually have a bound state. And so by adding in those microscopic details, you could add microscopic details to the model, replace your delta function with something a little bit more physical, and then the bound state, you could calculate the bound state energy. So kind of two different perspectives on what to do here. Either experimental input, you just think about this pole is coming from some experimentally measured bound state, or you have a better microscopic description of your system. Anyway, so the moral here is the following, at least the moral I take away from it, that the quantum theory is a bit sick. And to make sense of it, we need to introduce a scale, either from some experimental measurement or from improving the theory in some other way to obviate the need for this anomalous scale breaking. Very good. So that's my second example. And when I continue, we're going to talk about field theory. We're going to talk about scale anomalies, and more specifically, anomalies in the trace of the stress tensor in a quantum field theory context. So now for the third example in this lecture, we're going to talk about the trace anomaly, which is a form of scaling anomaly in a quantum field theory. A very simple quantum field theory. It's going to be a two-dimensional massless scalar field, but it's a very informative example, and I look forward to showing you the details. So here we go, a QFT example. We're going to be in 2 dimensions. I'll put a factor of a half because of convention, d2x d mu phi. That's my action. Now the claim is that this is scale invariant. If I send a position to lambda times the position, so I scale the distances between all points in the system in a constant way, so lambda is going to be a constant. The claim is that this action is invariant because, well, the derivative factors have a 1 over x, 2 of them in fact, 2 derivatives have 2 1 over x factors, and the d2x in the integrand cancels it. So the lambda dependence cancels out. This theory is scale invariant. So that's a sort of global scale invariance. And there's an idea here, it's akin to that idea I talked about at the beginning about being able to define a theory on any space-time, not just flat space. So here we started in flat space, could be flat Euclidean, could be flat Lorentzian, but there's an idea we should be able to promote that to a theory on any space and have some kind of cousin of that same scaling symmetry. So let's see how that might work here. So we have S is going to be 1/2, and now if I'm going to talk about any space, I need to introduce some kind of metric. So G is my metric, G with upper indices is my inverse metric, d mu phi d nu phi. So it's the same theory now in a curved space-time. And I've written this in a diffeomorphism invariant way so that it doesn't matter what coordinate system I use, I should find the same theory out again. And now, under that same scaling, what am I going to find? So g mu nu is going to transform under this scaling. It's a form of diffeomorphism. X mu goes to x prime mu is going to be lambda x mu. And what's my rule? Well, the primed metric I can write in terms of a Jacobian factor acting on the original unprimed metric, which in this particular case, if I've done my algebra right, it's 1 over lambda squared g mu nu. Because why? Well, because these derivatives dx alpha dx prime mu, these are just Kronecker delta functions with an extra inverse factor of that scaling constant lambda. So the metric transforms now. So I've added all these metric factors. I should be careful that I still have this scaling symmetry. Let's see what happens. So conveniently, the determinant of the metric has two factors of that lambda, because it's a two-dimensional metric. And the inverse metric transforms in the opposite way, as lambda squared instead of 1 over lambda squared. So this combination doesn't transform. Because why? Because g prime upper mu nu is lambda squared g upper mu nu, and det g prime is lambda inverse squared det g. And so the factors of lambda cancel out. This is an example of a more general kind of theory on a curved spacetime. It's an example of a Weyl invariant theory, at least classically. And that's going to be the whole point, that we're going to see a breaking of the symmetry quantum mechanically, an anomalous breaking. So what I mean by a Weyl transformation, I want to shift the metric by some factor. And in fact, it's convenient to make this local too, to make that function omega not just a constant now, but a function of space-time. And that's sort of more physical, right? It seems sort of unphysical to kind of acausally transform all of space at once. You could imagine locally scaling things and still hoping for it to be a symmetry. And then that information that you rescaled things locally could then propagate out. So it's a very simple example, this 2D massless scalar field. There's a more general set of scalar fields, so-called conformally coupled scalar fields, and I'll leave that as an exercise to you. It doesn't work quite as nicely in more than 2 dimensions. This is the conformally coupled scalar field. That if I write S equals, let's put a 1/2 there again, integral d dx, now I'm in d dimensions, I still have that square root of g, determinant of g, and now I'm going to have d phi squared plus a constant c, which I'm going to ask you to determine, the Ricci scalar, and phi squared again. And the claim is that this is, again, Weyl invariant if I scale now phi as well. So I didn't have to scale phi in 2 dimensions. It's dimensionless in 2 dimensions, but in general, there's a factor of d minus 2 over 2 times this Weyl factor. So if I supplement my Weyl transformation with this rule for the scalar, the claim is that there's a particular value for xi, which I'm going to ask you to determine in this exercise, for which this action is Weyl scaling invariant. All right. So even though it's classically invariant, the theory is going to have an anomaly, which by a slight abuse of notation, I'll call with various nomenclature, I'll call it a scale or Weyl or trace anomaly. And for the purposes of this lecture, it's all basically the same thing. So the trace anomaly. Where does this particular word come from? Why am I calling it a trace anomaly? Well, let's think about the definition of the stress tensor. So one very nice definition of a stress tensor in a curved spacetime is the response of the system to a variation of the metric. So if I have the response of my action, it's going to be integral d dx. Again, the square root of the determinant of g, I'll drop the determinant, but it's implicit t mu nu delta g mu nu, and I think conventionally there's also a factor of 1/2 here. So this is my definition of my stress tensor, t mu nu. Now, for Weyl variations, if it's classically a symmetry, then delta s should vanish. But I also have a particular form for what this delta g mu nu should be. It should be, what should it be? It should be 2 omega g mu nu. That's the infinitesimal shift in the metric under this Weyl rescaling. So if I go ahead and I plug that back into my definition of the stress tensor, what do I find? I find that classical Weyl invariance implies that the trace of the stress tensor vanishes. T mu equals 0. And there really is sort of a classical symmetry, classical discussion we could have here that go on for quite some time. But let me just point out in passing that there's also another current here we could define that's associated with the symmetry. We could write J mu is a space-time point x mu contracted with the stress tensor. And indeed that's conserved. Like if I take a derivative now, so this is the sort of flat limit of this discussion, then what do I find? I find a Kronecker delta plus x nu t mu d nu mu. And so what do I find? I find the trace of the stress tensor plus the divergence of the stress tensor, but we know the stress tensor should be conserved for diffeomorphism invariant theories. And so here's the flat space restatement of the fact of what the Noether current is for this Weyl invariant theory. So this is just an aside to maybe try and tie things into what you're a little bit more familiar with from a quantum field theory course and the consequences of having classical symmetries. Okay, so this is all aside. So this is what this trace anomaly is and how it connects into the scaling symmetry and Weyl invariance that we talked about on the previous page. Let's get back to our scalar in 2D to keep things nice and simple. Right, so I have my scalar action, 1/2 integral d2x, determinant g, d mu phi, d mu phi. And I want to try and show you an anomalous aspect, or where this anomaly comes from, or a way to kind of identify it. So in order to do that, I want to put this theory on a sphere, on an S2 of radius r, 0, to distinguish it from the Ricci scalar. And this is going to be a quantum theory, so we have to compute a partition function. So here's my partition function, or my path integral. Integrate over all field configurations, e to the minus s, which implicitly is a functional of my scalar field phi. And this is going to be Euclidean, so that everything is nice and well defined, or at least better defined. We'll see in a minute that there's an issue with this. Okay, so let's try and do this path integral on the sphere. Just like we did the path integral, or we identified the spectrum on this bead on a wire from before. Okay, so I have a Laplacian on a sphere. I want to identify the eigenmodes, but we know these, right? The eigenmodes on a sphere are just the spherical harmonics, these YLMs, which have the eigenvalues, which are the eigenvalues of the angular momentum operator for SO3. So box is really nothing but your friend L squared from quantum mechanics, and lambda is nothing but L times L plus 1, and we'll be a little bit careful about minus signs and the scale. We have to introduce the radius of the sphere, but that's what it is. And L is what you think. It's just 0, 1, 2. It's the angular momentum quantum number, and of course there's the degeneracy. There's an M as well. M can run from minus L to L, and so for each L, there's a degeneracy to L plus 1, right? Good, so we decompose our field into modes. These L and M modes. We have some coefficients Lm, CLm, and our eigenfunctions Lm, which I guess are going to be functions of our angles. We don't need to worry too much about their explicit form, but they're the YLMs, the spherical harmonic functions. So Z now is what? It's a path integral, which I can convert into an integral over all these coefficients, dCLm, product over L and M, e to the minus 1/2, sum on L and M, and now I'm using the fact that all those eigenfunctions are orthogonal to reduce it to a sum over Lm squared, and then I have this energy, L plus 1. And there was a factor of r squared as well, but that should cancel against the determinant in the integral, right? I also have this determinant. So what I get, right, is just this c squared. It's a real field. I don't need to worry about absolute value, or at least let's be sloppy about it. And so this is what's left. And now we'll do the Gaussian integral, and we'll write this as a product over our L and M modes, 2 pi over L times L plus 1. So often what people write is not the partition function itself, but its log or minus its log. We'll give that quantity a letter W, an effective action. And if I take a log of this thing, what do I find? I find 1/2 sum on L. I've got my degeneracy now because there's 2L plus 1 values of the energy that are all the same. And I have a log of what was in the square root before, L times L plus 1 over 2 pi. Great. So that's my answer. And it's clearly sick, right? This is clearly a divergent quantity, but like we did in the quantum mechanics example for scattering, we'd like to make some sense of it, to try and extract some physics. And I claim there is physics here to be extracted, and we'll get to that as we go forward. All right, so let's copy that and do our best to figure out what this sum means. So the first thing I want to do is rewrite that log in a slightly tricky way. This is a way people often call it the heat kernel method. It's sort of a tried and true way of trying to evaluate these kinds of divergent sums. So I've got integral. I'm going to replace that log with an integral from 0 to infinity dt over t e to the minus lt plus e to the minus l plus 1 t. So I claim that evaluates back to the log, where possibly I've discarded some constants, some infinite constants, but I'm not interested in those. And then next, what I'd like to do is I'd like to commute the sum and the integral, which is probably not a very safe thing to do since everything is kind of divergent, but let's do it anyway. And then I claim we can do that sum. That sum is just sort of a geometric series, or a derivative of a geometric series. And so I get dt over t, e to the t plus 1, e to the t minus 1 squared. And now I want to evaluate this somehow. It's still sick. I mean, I think you can sort of see that the limits, as t goes off to infinity and t goes to 0, there's some log or power law divergences, but it is what it is. We're going to do our best. So what we're interested in is we're interested in the UV behavior, which I claim is dominated by the t goes to 0 limit. And why do I say that? Well, because if you look at this initial rewriting, right, as t goes to 0, the larger and larger values of L get to contribute more. They're not killed off as fast. And the larger values of L correspond to higher harmonics, they correspond to higher energy states, and so it's the UV of the theory. Whereas large T would cancel the high L's very quickly, and so it would be dominated by the IR limit of this system. So I'm interested in the UV limit, just like we were in the case of this 2D scattering in quantum mechanics. So in that limit, there's a power law divergence, goes as 1 over t squared, and then there's a log divergence, and then there's finite bits. This is a small t expansion of the integrand. And I claim that this piece doesn't really contain any physical information. It's regulator dependent. It's very sensitive to how we set up the theory. But this 1/3, on the other hand, does contain physical information. So let's think about that. So this is our result. Let's call it W. Let's copy it to the next page. Where's the physics in this t? So this t inverse, I claim I can think of as the radius of the sphere times this UV cutoff that I've added in. Small t is the UV behavior, so large 1 over t should also be UV behavior. And so by cutting off at small t, I'm introducing some UV regulator, some UV mass regulator. Okay, so if I plug that in to what's going on above, I'm going to find minus 2 r0 squared lambda UV squared minus 1/3 log r0 lambda UV plus finite terms. And so now there's an explicit scale dependence in this theory that wasn't there before. Remember, I just put in the radius of the sphere by hand. And now to make sense of this partition function, I also have to introduce not just this IR scale, which is the radius of the sphere, but a UV scale as well. And so what I'm finding here is that the partition function has a scale dependence, that lambda UV times the derivative lambda UV acting on the log of the partition function is minus 1/3. That's this particular term here. Whereas this guy here, I claim I can remove. Just like I was removing things in that first example of the bead on the wire where I had that integral A, which was a counterterm. Here there's a slightly different counterterm I can add. I can add integral d2x square root g with some arbitrary coefficient. So in our earlier example we called it k. Let's call it k again. I can tune this k to cancel this term here. Now both scale with the radius squared of the sphere, right? This is some sort of volume term for the sphere, and to make it dimensionless, I need k to go as some UV cutoff, and so I can tune k to be lambda UV squared and cancel that piece here. But there's no way I can add that counter term to cancel that piece. That's the claim. The coefficient here means something. I can shift what's inside the log by some by something, but we'll just shift everything by an overall constant. But the 1/3 multiplying the log has a physical meaning. That's our anomaly. So more generally, for 2D theories that are Weyl invariant, what we expect is the following. We expect lambda d lambda of w be minus c over 24 pi. So the choice of normalization here, that 24 pi is just purely convention. You'll see why I might have chosen it in a minute. This is the Ricci scalar because it doesn't have that naught, square root of the determinant d2x. So again, this is the Ricci scalar, no longer the radius of the sphere. Okay, so let's see what happens for us, for our scalar field on the S2. So the Ricci scalar should be 2 over r naught squared for an S2. And the volume of our S2 should be 4 pi r naught squared. So the r naught, the radius factors cancel out. And this whole thing evaluates then to minus c over 3, which if I compare with my result on the previous page means that c equals 1. C equals 1 for a free scalar. So that's why we chose the normalization the way we did, so that the free scalar would have c equals 1. This often gets rephrased in a local form, so not as an integral, that the trace of the stress tensor, if I vary this effective action with respect to rescalings of the metric, I should get the trace, that this should go as c over 24 pi times the Ricci scalar. So that's a sort of standard result for 2D conformal field theories or 2D Weyl invariant theories. Okay, so why is this such a big deal? Why do people care about this? What can you get from it? Well, let's follow this a little bit further. So far what I've told you is what the scale variation of the action is. And let's try and find out what can we find out what the effective action itself is, the action itself that governs the anomaly. Can we integrate this expression for the derivative of w? Because that might tell us all sorts of stuff about correlation functions, right? This effective action is a useful tool for generating correlation functions. And indeed in this 2D case it is possible to integrate w to get this anomaly effective action, which is going to tell us all kinds of interesting things about correlation functions, in particular of the stress tensor. So w, claim I can integrate this, I'm going to get c over 24 pi. I'll just give you the answer and you can sort of go backwards and see how it must work. R times tau minus d tau squared. Now what is this tau? Why did I introduce it? Well, it turns out that the effective action itself is non-local, and so it's useful to give it a local presentation by introducing this additional massless field tau, often called the dilaton. And we can see how this gives us the right answer if we invoke the following transformation rule. So if we rescale g mu nu by e to the 2 sigma g mu nu, we rescale tau by tau plus sigma, and then I'll leave you to derive this. The Ricci scalar should transform as e to the minus 2 sigma r minus 2 box sigma. So this is something, again, special about 2D and higher dimensions. The transformation rule is a bit more complicated for the Ricci scalar. But if I have these in hand, I can see quite clearly that the Weyl variation of this effective action gives me the right answer, what I had before. This d2x root g r delta sigma. And how do I see that? Well, let's just look. I mean, basically this whole term comes from the tau variation of the first term. If I vary r, I get box sigma, and if I vary this d tau, I get a tau plus sigma term. And so you can sort of see that the box sigma tau term from the first piece will cancel the, after integration by parts, a d tau d sigma term in the second piece. And so it's fairly straightforward to get back and forth from, or at least to get back from this expression to the variation, the proper variation. It's like a differential equation. Once you found the solution, you can check that it's right. It doesn't matter how you found it. Although there are various constructive ways to make these things, I won't go through that here. So this is the answer. And now again, you're saying, well, what is this dilaton? Do we really need it there? Well, let's try and get rid of it and see what happens. So the equation of motion for the dilaton is what? It's 2 box tau, if I've done this right, is equal to minus r, or more particularly tau by abusive notation is minus a half 1 over box times r. So if I plug that back up into the effective action, what I'm going to find is that w is c over 24 pi. I think there's a factor of minus a quarter, although I could have fooled myself. d2x square root g r 1 over box R. So that fact I have a 1 over box there is telling me it's non-local. And this has a name. This is often called the Polyakov action in conformal field theory. And it's quite interesting that it's going to generate now the anomalous behavior in all stress tensor correlation functions. Just by varying this with respect to the metric, you should find the way in which all these stress tensor correlation functions break scale invariance. And in fact, it makes sense even to claim that it generates all of these stress tensor correlation functions completely, because it turns out in these 2D contexts, all of the stress tensor correlation functions are fixed once you know the central charge C, once you know this number C. So there's a sense in which this effective action tells you everything about the stress tensor sector of your 2D theory. So, remarks. It's a sense in which W generates all T mu nu correlation functions, and not just in flat space, but on a general metric. And in particular, it's going to generate the 1-point function on a general metric. And this is closely related to this Schwartzian derivative. From this action, I'll leave this as an exercise. From this action, you can show how T mu nu transforms under Weyl transformations. So if you have the stress tensor in one frame, then you can find it in all other frames that are related to the original metric by some Weyl transformation. And then I'll give you one last cute example. So we know that we can put a field theory at non-zero temperature by wrapping the time direction on a Euclidean circle. And so this Schwartzian derivative business can be used to show how the energy density of one of these theories behaves. That it's going to go as the central charge C times the temperature squared over 6. And again, you do this by going to a metric where the time direction is compactified. And that periodicity of the time direction gives you the temperature. So in this particular case, this effective action and knowledge of the central charge C gives you an enormous amount of information about this 2D theory. So you begin to see some of the power behind this anomaly approach to quantum field theory. Okay, so my last and final example, which is coming right up, is going to be QFT with a boundary. So now in this last and final example, I would like to talk about some physics that's very close to the research that I've been doing in recent years. And in fact, the particular result I'm going to discuss today you can find in a paper we wrote about 3 years ago. I think it's a very nice example, and I hope you do too. So QFT with a boundary. So we're going to let this 2D system that we had in the previous example now be a surface or boundary in some larger 3D system. So we're going to let the 2D surface be a boundary of a 3D system. And we're going to ask, what is this anomalous variation of the effective action now? What could it be? And now, to try and figure out what it must be, we're going to use a very powerful criterion which was invoked by Wess and Zimino first, I guess. So this is called Wess-Zimino consistency in honor of them. They used it in the case of these gauge theory anomalies in non-abelian symmetry groups, where it's actually a little bit more intricate because things are non-commuting. For us, it's particularly simple because this Weyl variation, these delta sigmas, they generate an abelian group. And so it must be that if we take two of these Weyl variations, it doesn't matter which order we take them in. Whichever order we take them in, we should get the same thing. And so they should commute. Their action should commute. And the other thing we want to do to kind of constrain what this anomalous variation which should be, we're going to use local counterterms just like we've been using up to this point to separate what's physical from what's not. We're going to use local counterterms in W to simplify the anomalous scale variation. So if we find some variation that looks particularly complicated, sometimes we can get rid of some of that. Just like we saw in the case of the scalar field on a sphere a few moments ago, we can use these local counterterms to get rid of some of that extra stuff. So this is going to be a scale invariant or Weyl invariant theory, at least classically. And we can invoke that now because it means the possible stuff that can appear in this scale variation is rather limited. So we're going to construct words from the metric. And now that this 2D system is a surface, we also have a normal derivative, a normal vector. And we'll make sure it's unit normalized, so n squared is 1. We're going to construct words from the metric and this normal vector that are second order in derivatives because otherwise we need some dimensional constant, which we don't have, because if we had it, then the theory wouldn't be scale invariant. Like if we had a mass, then that would set some scale, the theory wouldn't be scale invariant. So we're forced to look for some anomalous variations in things that are second order derivatives. Okay, so we're thinking about this 2D system now as a boundary. So let's develop a little bit more formalism for this. So we need some sort of notion of a boundary metric. Really, it's going to be a projector, at least in the context of the current rather crude discussion. So I'm going to have a boundary metric, which is the ordinary metric minus the normal derivatives. And since it's a surface, I can also talk about extrinsic curvature. It's another useful gadget to work with. It has nice covariance properties. So the extrinsic curvature I can define as a projected version of a covariant derivative of this normal vector. So it has only tangential indices, the extrinsic curvature. So these are some ingredients that go into this construction. And now, what's my word list? Well, what can I write down? I've got a 2D Ricci scalar, like I did before, so that's probably still going to be there. I can construct things that are quadratic in the extrinsic curvature, or I could take a trace of the extrinsic curvature first. So by k, I just mean k mu nu, h mu nu, so traced over the tangential directions. What else can I do? Well, I could have k and then a normal derivative. I could have two normal derivatives, and I could have, say, a normal derivative acting on the extrinsic curvature. You know, everywhere here I should also have my little Weil variation parameter sigma. So some of these terms I've got derivatives acting on sigma, other terms I don't. And I'll just point out that the places where I don't have a derivative acting on sigma, so these guys, these are good candidates for counter terms, because I could add those to the original action without this extra Weil parameter sigma, and think about Weil variations of those to remove terms from partial sigma of the effective action. Oh, and I missed one here. There's one more here I should write down. I can think about a two-dimensional Laplacian acting on sigma as well. So let's see, I've got 1, 2, 3, 4, 5, 6, 7 terms that are second order derivatives that could show up in the Weil variation of the effective action, the anomalous Weil variation of the effective action. So in other words, well, let's copy it since I've run out of room. So in other words, delta sigma w should be a sum of these words, or could be a sum of these words. We have got to figure it out. So before I go forward, I want to simplify my life a little bit, and I want to introduce a traceless version of the extrinsic curvature. So in our particular case, this is just a two-dimensional boundary, so there's a factor of a half there. And I'll trade the appearance of the extrinsic curvature here for the traceless one in my words moving forward. So there's some tedious work to do, figuring out what the Weil variation does to all of these terms, and I'll leave a lot of it as an exercise to see that we're going to be varying these covariant derivatives, so we need to know how to vary the connection. So we need to know that this is some derivatives acting on the Weil parameter. We need to know how Weil variation acts on the normal derivatives. These are all infinitesimal Weil variations, so sigma is a small parameter in all of this, minus sigma and mu. So the fact that you have to contract with the metric is going to shift the sign there. I need to know how delta k shifts. So that leading term is just the fact that it's a first order derivative, but then there's some derivative pieces that make my life a little bit miserable here. It means it's not completely covariant in the way it shifts. So that's three of them, and then we can keep going. I need also the trace, the variation of the trace is minus sigma k plus 2n lambda d lambda sigma. That I need the trace, the variation of the Ricci scalar. This is the two-dimensional Ricci scalar, minus 2 sigma r minus 4 box sigma. I need to know that the variation of the 2D box is just minus 2 sigma, so it's covariant. And I think that's it. So you've got to do all these sort of building block calculations to see what's going on. And then from this, we can find the following transformation rules for these words that we had in the potential anomaly action. So we're going to see now that delta sigma of k squared, I don't really care about constants here. Let's just sort of see the general structure. So this is going to give me a k and then a n mu d mu sigma, just based on what we had on the top line there. And from the previous page, so if we vary something with a normal derivative acting on k, then I think I get the same thing back after commuting some derivatives through the normal vectors, and we also get a second normal derivative. And so what we're seeing now from this is that we can cancel. So the claim is that if this term showed up in the anomaly effective action, we could cancel it by adding a counter term of the form k squared. And if this second derivative showed up in the anomaly effective action, we could cancel it by adding some combination of these two terms. So we don't expect to see either this piece or this word in the anomaly effective action. We can cancel them by counter terms. And another thing to note is that you could wonder now, could these terms k squared and n mu d mu k themselves show up in d sigma w? And the answer is they can't, because when we vary them, if these things showed up themselves, they would involve normal derivatives acting on sigma, and so they wouldn't be Wess-Zumino consistent. We couldn't integrate by parts to make the two sigmas appear in a symmetric way. One would appear with a normal derivative, one wouldn't, and their commutator wouldn't vanish. So, by doing this simple computation, we've ruled out all of these possible structures from the anomaly effective action. We've ruled out 4 of the structures. And another thing we see is if we have this rule for delta r, we see box sigma showing up on the right-hand side. I mean, the 2 sigma is just going to cancel against the determinant of the metric. And so this is the piece we have to care about, this derivative acting on sigma. And so we see that even though the box sigma is Wess-Zumino consistent on its own, it can be canceled by a counter term, by adding the Ricci scalar itself to the original effective action. And so if we look back at our original list on the previous page, it boils down to something fairly simple. We've gone and we've basically not allowed ourselves to have this term, this term, this term, this term, or this term in the anomaly effective action. We're just left with 2 possibilities, this k hat squared piece and r sigma. And indeed, we can look at that now and see if this makes sense. So we're left with only this 2D Ricci scalar times sigma and this traceless version of the extrinsic curvature times sigma for the anomaly effective action. That del sigma of w is integral d2x square root g a r2d, where that a is some constant, and then b k hat mu nu sigma. Right, so let's think about these 2 bits and see whether this is really a consistent effective action. Doesn't look like we can cancel any of it with counter terms. Is it Wess-Zumino consistent? That's the question. So this piece is going to transform to a sigma box sigma prime, where this is the 2D box. So we can integrate that by parts. And so it looks Wess-Zumino consistent provided a is constant. Provided a is constant, we can integrate by parts, and we can make the sigma and sigma prime appear in a symmetric way. And so the order of operations here, whether we act with sigma or sigma prime first, it doesn't matter. And this guy, this k hat squared term, it turns out to be Weyl invariant, or Weyl covariant, if you will, on its own. And so it's sort of trivially Wess-Zumino consistent, because the second variation just vanishes. And so it doesn't matter whether you symmetrize or not, it just doesn't give you anything. So these are the 2 pieces that appear in the anomaly for a 2D boundary of a 3D system that starts out being Weyl invariant. This is the boundary anomaly for a 2D Weyl invariant boundary in a 3D system. So I'll give you an exercise. It's to consider, it's actually not massless now, it's conformally coupled, 3D scalar field on a hemisphere, 3D hemisphere, and you're instructed to use both Neumann. There's 2 cases to consider, so use both Neumann and Dirac boundary conditions. Compute the partition function like we did for the scalar field on an S2, and extract from this the A coefficient. You don't have to worry about B in this case, since we're working on a hemisphere. The extrinsic curvature on that equator is going to vanish, and so there will be no contribution from this B term to the anomaly in this case. And you can use the hemisphere to figure out what A is in these two cases. So it's a rather challenging example, but it follows along the same line as this massless scalar field on an S2. And so I hope you can, if you're ambitious, you can work your way to the end of it. Now for B, we need a little more development than I provided so far. So let's back up and talk a little bit about some aspects of these 3D violin invariant systems with 2D boundaries. In particular, I need to introduce a concept that's called the displacement operator. Okay, so fresh page for that. We're almost at the end here. Just got 2 more pages in my notes and 1 more exercise, and then it's done. So here's my variation of my effective action. I have a 3D bulk with a metric, and as we discussed before, we can define the stress tensor as the response of the system to a variation in the metric. And now I also have a 2D boundary, and you can ask, here's my 2D metric on the boundary, what is the response of the system to a variation of the location of the boundary? So this is the location of the boundary, and this response has a name. This is what's called the displacement operator. So the location of the boundary is a source for the displacement operator. So I want to consider 2 kinds of symmetries in this system. We'll consider bulk diffeomorphisms, so changes of variable under which x mu goes to x mu plus some small displacement that's a function of position. And we know under this kind of transformation that the metric varies as covariant derivatives of this displacement, epsilon. And the stress tensor is typically conserved, but in this case, because we have this displacement operator, and because x varies, the location of the boundary varies in response to diffeomorphisms, there's a spoilage here of conservation of the stress tensor. There's a delta function that localizes on the boundary, and what I find here on the right-hand side is the displacement operator. So the displacement operator has another definition, if you will. It's the failure of translation invariance. So that's bulk, and I also want to consider boundary diffeos. So I have some coordinate system on the boundary, ua plus kappa au, and under a change of variables now, I'm going to shift, under these diffeomorphisms, x will shift in the following way. And so what does this imply? It implies that ka dax mu d mu equals 0. These diffeomorphisms only affect the boundary term, and this thing that's multiplying the displacement operator, this is purely tangential, right? There's no way for the diffeomorphisms on the boundary to affect the bulk, and so this also implies that the displacement operator only has 1 component here, as only a normal component. What do I have here now? I have d mu t mu nu is delta of xn d nu, and this is only non-zero for nu equals n. The only non-zero component is the normal component. And there's a little sort of Gaussian pillbox argument you can run for this that will show you yet one more way of thinking about the displacement operator in this context. So if I take the boundary limit of the normal component of the stress tensor, that is also the displacement operator, which is a useful fact for doing the last exercise I'm going to assign. You can use the stress tensor, the boundary limit of the stress tensor, to define the displacement operator. It's like that problem one does in electricity and magnetism, where you have a charged capacitor plate, and you can relate the normal component of the electric field to the charge density on the plate. It's basically the same computation. Okay, so let's try to relate this B coefficient to something about the displacement operator, if we can. That'll be our last goal in these lectures, and then we will wrap things up. So I'm going to consider the extrinsic curvature, which we said was the covariant derivative of the normal vector, and we want to do this for a nearly flat boundary. So xn, we'll put the boundary at xn equals 0, and that will be basically where the boundary is up to small corrections. And because of that, the normal vector takes the following form. It's going to have a 1 in the normal direction, and then all the other components are just these small derivatives of the normal coordinate with respect to the tangential directions of the embedding. So this thing at the top, this is the capital X, and this is a lowercase x. So what does this imply? From our definition of the extrinsic curvature, this is going to imply that KAB, the tangential components of the extrinsic curvature, I can write at least approximately as a Hessian of this normal embedding coordinate. And moreover, this Weil invariant k hat squared, if I expand it all out, it's at least approximately d squared xn dxa dxb minus a half delta ab, the 2D box, which is basically just a Laplacian. This whole thing squared, and if I work this whole thing out, this is basically xn box squared 2D xn after possibly some integration by parts. Okay, so that's a nice simple expression for this Weyl invariant k hat squared in the presence of a nearly flat boundary. And I hope you can see where I'm going with this. The idea is to have re-expressed it in terms of this embedding coordinate, so I can then make a connection with the displacement operator. So if I go back to my anomalous variation of the action, the b term here I can write now as b over 2 integral d2x xn box squared 2dxn, which implies that I'm also going to get an anomalous variation of the 2-point function for the displacement operator. If I just vary the above expression twice with respect to xn, that's going to give me the 2-point function. And so what is this? This is b over 2 box squared 2d delta 2 of x. Almost there. Now, note the following thing about the displacement operator in a Weyl invariant or a conformally invariant theory, that it's determined by the symmetries. So here I'm basically in half of flat space. It's determined by conformal symmetries to be a number divided by the distance between the insertions up to the 4th power. This is fixed by conformal invariance. So I effectively have some kind of like 2D conformal field theory living on this surface, and the correlation functions of operators that are restricted to that surface have to obey those symmetry properties. And now to get at the relation between B and CDD, I'm going to use some tricks. It's sometimes called real space renormalization. So what we'll do is the following. We're going to rewrite 1 over x to the 4th in terms of logarithms as a 3rd power of box log lambda squared x squared squared. And there's our scale dependence entering. This implies lambda d lambda 1 over x to the 4th is pi over 32 box 2d delta of 2x. We just follow our nose here basically. We're using, we take the lambda derivative, that's straightforward to do, but we're also using the fact that the Laplacian acting on a log in 2 dimensions is a Dirac delta function. This is a fact that you may have come across originally in electricity and magnetism, that wires make log potentials, but it's important here for developing this connection. And so now we're basically done, because we have a way of introducing or identifying some scale dependence in this correlation function. People often talk about how the fact that at x equals 0, it's not well defined. There's an infinity, that you need some way of regulating it. And this is a sort of partial way of regulating it by introducing this lambda. And now by comparing the scale variation of the 1 over x to the 4th with the Weyl variation of the action up top, we at last get a relation between b and c. And that's where I'll end things, with the fact that pi cdd over 32 is equal to b over 2. So there it is. That's my last example, and thanks for bearing with me so far. I almost forgot to give you my last exercise, so let me do that before we wrap up. This is an exercise to compute this central charge B in a simple case. So consider a conformally coupled scalar field in 3 dimensions. So that's that action I gave you as a previous exercise from a few minutes back. Let's do this on a flat half space, so the boundary will be flat. And let's also specify both Dirichlet and Neumann boundary conditions. So there's sort of 2 subcases to consider. One subcase with Dirichlet and one subcase with Neumann boundary conditions. And you'll have to see whether the answer is the same or different in each case. Okay, so what I'd like you to do then is compute the displacement 2-point function in both of these cases. And from the coefficient of this function, it's fixed up to one number by conformal invariance. From the coefficient of that number, determine b. And there'll be an intermediate step here. There'll be an intermediate step where you're going to have to compute, or at least this is the way I did it, compute the normal component of the stress tensor, of the improved stress tensor. So that's the exercise. Let's see how you do with it. Okay, so that brings me to the end. Let's just wrap up and sum up what we've done in this rather long lecture. We've considered 4 examples of anomalies. Our first example was a bead on a circular wire. This was an example of a Tuft anomaly, an anomaly that showed up once you introduced external gauge fields. And I mentioned in passing that it's a nice example to build intuition for more complicated examples more complicated examples with actual practical interest, like the theta angle in Yang-Mills theory. Our second example was scattering off a attractive delta function in 2D quantum mechanics. It had to be two-dimensional, or else I didn't have a scaling symmetry, classical scaling symmetry. And we saw this was a quantum mechanical example of a scale anomaly. And then we had two quantum field theory examples. We discussed the trace anomaly for a 2D massless scalar field, a relatively famous example. And then finally, I discussed some more recent work about boundary trace anomalies. So this is a quantum field theory now with a boundary. You can have a purely boundary contribution to the anomaly, and we focused mostly on a 3D, 2D system. So I've shied away from precise definitions in this lecture, instead focusing attention on examples. And I chose these examples so I hope that I could develop some better intuitive sense of what an anomaly is. That's what I hope you'll leave this lecture with, is a better intuitive sense of what is an anomaly. So thanks for your attention.